Thank you. Thank you very much for coming. I'm very pleased to welcome the Dean of the Faculty of Science, Professor Ibrahim. I've been practicing this and I got it wrong. I'm only yet. He's going to give the welcome. Thank you.
Thank you. Good morning, colleagues. That sounded like a graduation. That happened a few days ago where all the names come. Obviously you have different names. You have African names and different cultural names. And suddenly there's a Smith and a Jones and a Mamonian in between. So thank you for that. I'd like to welcome you to Wits University. I hope you have an exciting day. As Dean of the Faculty, I have a very interesting job. 90% of the time it's spent being a referee. I'm sure many things will tell you that. But the 10% is spent looking at the development of lots of interesting projects. And material science is one of them. I think over the past year or so, we've seen lots of interesting things happening in this discipline. And one of the interesting things is that we've just had a very strong partnership between the Faculty of Science and the Faculty of Engineering through the Center for Strong Materials. But we also have a partnership that we told you with Brookhaven National Labs in the US. And we actually have a team that just got back from Brookhaven. And the interesting thing for me is the feedback that the team gave me, because this is not my field. I'm a mathematician. So I always get teased when we sit at budget meetings, because when the price of your equipment comes to the budget committee, I just see all the zeros. And my budget is usually just either a laptop or a pen and a piece of paper. But at Brookhaven, their budget for their lab is probably the budget of our country. And that's probably their recurring budget. So that's what it cost us to run the lab, not the new equipment that we're getting. But what was interesting is some of the material scientists who went with were telling me that some of the experiments that we run at BITS, for example, that may take, I don't know, 1 or 2 hours to run, they now can do in a few seconds at Brookhaven. So in terms of cutting edge research, they don't only do in time linear, so vertically down the material, but also across the materials, cross sections. And that takes a few seconds to run. So they don't only run samples per second, and you can do multiple samples. And one of the things that our partnership is looking to establish is that we can actually do remote experiments, because that's what the system they're setting up. And in fact, it means that as students and staff, you don't even have to leave your office. You literally just need to send your samples to the laboratory and run the experiment from your office. And what that requires, in fact, for South Africa is high internet speeds and lots and lots of data space, because where your samples generate a few gigabytes, you're now looking at terabytes of data being generated. So the message that came back from their visit was that data science, artificial intelligence, machine learning, and material science, nanotechnology are all becoming one discipline. And in fact, that's what we see in our faculty, is that the intersection of many disciplines are coming together at very high levels of research. And in fact, this is happening across the university. So if you want to be a doctor at WITS, you can now be an engineer first. So we have our chem program where many of the doctors graduate into medical program engineers. So your doctor of the future will probably be a mechanical engineer, which is a scary thought, because I don't know if you know many mechanical engineers or chemical engineers, but that's probably going to happen. So that's something to think about for those of you embarking on a PhD. It's where is your discipline going to be in the next 5 to 10 years? Right? It's probably going to be working with a computer scientist, working with someone who's in a completely different discipline to you. And it's probably going to be someone in a different faculty in terms of how we structure our universities. course, if you were to go to a different institution, they don't structure programs the way we do. They structure them around themes. So you would be able to work with some themes on this. So I leave you with that message, because it's a sobering thought for me, because the number of zeros at the end of the budgets just keep on growing. So when Ian Jankel and I meet each time to discuss budgets, and we see what strong materials and various centers ask for, the zeros just keep on adding up. Because now it's not just equipment, it's computers, it's this, it's that. But it's an exciting future for us, because it does mean that you as young South Africans are not far off. Right? It means you can go and work in a laboratory across the world, and you can compete with top scientists. All you need is the opportunity. And we're hoping these partnerships will give you that opportunity. So please continue doing what you're doing. And remember that the opportunities are there. You just need to grab them with both hands. And not be afraid, because you can compete. So good luck, enjoy your day. I think we end at about 12 o'clock, if I'm not mistaken. And I'm sure we will feed you. I think that's the one thing that is good at. You will starve before you leave. We make you pay for it though, because you will be speaking a lot. But do enjoy your day. And on behalf of Ian Jankel and myself, welcome to it. Thank you. So, like a good dean, I will disappear, but we have good people taking care of you.
Thank you very much. It's 12:15.
Oh, 12.
Thank you. Right. The first focus area to present results is carbides and cermets, and Professor Natasha Sachs is going to introduce it.
Good morning, everyone. I'm the Focus Area Coordinator for Carbides and Cermets, as Leslie has mentioned, and I'm just going to briefly tell you who make up carbides and cermets in terms of staff and students, and by the students you'll see what kind of projects are done. So just to give you an initial introduction into what carbides and cermets look at, the research focus is based on tungsten carbides, which are a very hard and refractory set of materials, and they're made through powder metallurgy means in the same way that ceramics are. And tungsten carbides, we look at either sintered coatings or sintered alloys or coatings, where tungsten carbide is the predominant carbide, and we then add other carbides to it, and it is normally cemented together by cobalt, which is the dominant binder, and that's just because cobalt wets tungsten carbide the best when it becomes a liquid during the sintering temperatures. But cobalt has some carcinogenic health issues worldwide, so there has been a drive to replace it with either iron or nickel binders. So a lot of the research which started out with cobalt binders has moved focus over the last few years to focus more on nickel and to a smaller extent on iron. Tungsten carbide itself, which is a very wear-resistant material, gets that from its hard grains. Now the grain size, the smaller you make it, the better it becomes. So they tend to use what is called grain refiners, which are typically chromium, tantalum, niobium, and titanium and vanadium to the material in carbide form in order to make the grains smaller. Now, additions such as titanium and tantalum are also added to the materials when you are machining things like steel, which require a very different type of material to machine it compared to when you are machining titanium, which we know is a very finicky kind of material to machine. And we also do cermet research, which then tungsten carbide doesn't form the main constituent, but we look at alternative carbides or a range of mixed carbides in different proportions, and they mainly make up titanium, tantalum, niobium, chromium, and molybdenum carbides, which are added. Some of them are added because they improve the corrosion resistance of the material, apart from improving the ductility and transverse rupture strength. South Africa is a primary producer of vanadium and ruthenium, and so to some extent we try to add vanadium and ruthenium in increasing with different amounts to the material in order to provide some kind of economy for a primary resource in South Africa. So some of the researchers add them in various forms to either the alloys or the coatings. The researchers, in terms of the staff members, the director forms part of I think it was all focus areas, if I'm not mistaken. And then we have Professor Einol Botev and Professor Claudia Polesev from Mechanical and Industrial Aeronautical Engineering. Then from Chemical and Metallurgical Engineering, we've got Dr. Josias van der Merwe and Dr. David Whitefield, who are mainly metallurgists. And then we also from Metallurgical Engineering is Professor Sello Ndlovu, who is the Sarchi Chair in Hydrometallurgy and Sustainable Development. We then also had Dr. Rodney Genga, who used to be a student in CASE, then became a postdoc fellow, and in the last year was appointed the director of the Academic Development Unit at WITS in the engineering faculty. We then also have a collaboration at Stellenbosch University with Dr. Tiaan Oosterhuizen in industrial engineering, where we do a lot of machining projects together with him. Stress analysis is mainly done at NEXA through our collaborator, Dr. Andrew Venter. And then Dr. Mira Topic from Itemba Labs, who make use of analytical facilities in Somerset West, and she's collaborated on a few projects to add her range of expertise. Then in the past year, the postdoctoral fellow, Dr. Perawat Ninthavarawan, went back to Thailand. He left in May. He completed his 2-year stint. He was an academic in Thailand, and he was given a 2-year sabbatical to come and be a postdoc fellow at WITS. At the end, when he returned, I was invited to go back to Thailand with him for 3 weeks, and through that we established a memorandum of understanding as well as a legal framework to allow exchange of staff, students, and even samples between his university in Thailand and WITS, and that is not exclusive to my focus area. It's open to anyone in engineering and science who wants to make use of facilities at King Muktat University of Technology in North Bangkok. You're more than welcome to make use of the agreement in order to make that exchange. They have some very impressive facilities over there for both science and engineering, and they have extensive collaborations with a lot of European universities, especially from Germany and France, so it's well worth looking into. Then, as of yesterday, a new postdoctoral fellow joined our group, and that's Dr. Gertrude Fomer. She was a postdoc at Rhodes University, and her term ended there, and so she'll be working on tribocorrosion of hard metals. Okay, those are the academics. Student members, we only had one who graduated last year. That was Jacqueline Carascio, who did her work on recycling of tool materials. And then Dominic Smith submitted his MSc for examination at the end of last year, beginning of this year, so that's currently under examination. The current students range of MScs and PhDs. By their names and their topics, they tell you the range of research that we do. So based on what they're doing, we essentially do a lot of cold spray coating work with Professor Einol Botev. So some of them are looking at the effects of different feedstock powders, others are adding the influence of ruthenium or niobium in order to improve the properties. Some of the students, and one of them you'll be hearing was the main speaker today, working with the Sarchi Chair, are looking at alternative and more environmentally friendly recycling methods for the tungsten carbide materials. Then we have a range of students looking at additive manufacturing. And additive manufacturing in the last few years has just taken off astronomically and on a global scale, and South Africa can't lag behind. So in terms of manufacturing, we've been looking at different laser products from both Stellenbosch University as well as the CSIR to try different additive manufacturing techniques in order to make these materials as well so that we can compete. And the good thing is on a global scale, nobody's gotten it right yet with hard metals, so we're all in the race to try and get viable products using additive manufacturing. Then we do a lot of machining studies as well, and that's done with Stellenbosch University as well as mechanical engineering here. We've got people like Rodney and them developing new tools where they're making niobium carbide the main constituent, and then using things like laser shock peening in order to improve the properties of the cutting tools themselves. Okay, so those are the range of projects as well as students who are there. We've got 4 students based at Stellenbosch University, and all the rest are based at WITS. The last 2 are new MSc students who started in January this year. Okay, and that's a brief introduction to CASE, what we do, who we are. And now I'd like to introduce Mr. Alan Shelley, who is going to give a talk. He is a PhD student in the school, being mainly supervised by Professor Sello Ndlovu. I'm the co-supervisor, and he's looking at alternative methods of recycling tungsten carbide, and I'm sure he'll tell you more about that. Thank you.
Good morning, everyone. My name is Alan Shemi, and I'm here to talk to you about the scrap recycling of tungsten carbide using an acid leach process. And my presentation outline is as shown there. I'll begin with introduction, look at the aims and objectives, materials and methods, and then I'll look at the results and discussion, from which I'll draw my conclusions. Over the years, there's been a steady increase in the global demand for tungsten, and this could be attributed to the unique properties of tungsten, which are utilized in the making of tools and wear parts. Looking at the production figures and the price of tungsten, we see that this actually is a billion-dollar industry. However, there is not much tungsten deposits out there in the world, and hence the need to preserve the finite resources of tungsten. There are several industrial products that can be made from tungsten, and among these, cemented carbide accounts for approximately 60% of the industrial products made from tungsten. And cemented carbide really is a versatile hard material useful in engineering and tooling applications. Cemented carbide is widely applied in industry as displayed here in these various sectors. But then we see that when the tools and wear parts get worn out and get rejected from industry, as well as from the production process, these materials become available as secondary tungsten resources. Looking at the tungsten material flow, we see that approximately, say, 4% of secondary tungsten, 4% of total tungsten demand comes from secondary tungsten. This goes to show that secondary tungsten plays a very important role in the supply and demand of tungsten raw materials. Current recycling methods are basically three: the direct method, the indirect method, and the semi-direct method. One of the methods that has found wide industrial applications is the zinc process. These processes, however, these recycling methods, however, have got quite a number of disadvantages, such as high energy requirements, the incomplete separation of the tungsten monocarbide from the binder metal, long reaction times. We see also that there are slow process kinetics, passivation, and high reagent consumption. Our project aim, therefore, is to combat the disadvantages that we have seen in terms of low energy requirement, low environmental impact, recovery of the tungsten monocarbide and other valuable metals, reagent regeneration, and reduced reaction times. Our project objectives are as follows. The first one being we want to look at the effect of the parameters. We want to investigate the parameters and how they influence the cemented carbide dissolution. We also want to look at the physical and chemical properties so that we may understand the limitations of the process. We also want to derive the reaction kinetic model, which describes the cemented carbide dissolution process. We also want to look at the cost implications as well as the conditions that are favorable for reagent regeneration. Our materials are production scrap buttons, shown in the top corner there. And the selection of our reagents was basically based on the thermodynamic feasibility, a critical study of the thermodynamic feasibility of the hard metals in aqueous media. From the Pouget diagram, the one in the top left corner there, we see that cobalt dissolution requires oxidative acidic conditions, leaching conditions. However, under those conditions, we see that there is likely to be a formation of the tungsten, insoluble tungsten oxides. These could actually cause a problem during cobalt dissolution. These are our key reactions. And our main concern here is reaction 4 to 7. Under these reactions, we see that there is a formation of insoluble tungsten oxides, which are likely to actually cause passivation during leaching. And so we came up with an intervention plan by introducing a complexation agent which would react with tungsten to cause tungsten to become a soluble complex. And by so doing, reactions 4 to 7 would actually be inhibited. Our new approach in terms of the foregoing is that among the 3 recycling methods, that is direct, indirect, and semi-direct, we see that we chose to prefer the semi-direct method through selective leaching. As for the complexic agents, the good candidates were tartaric, maleic, and citric acid. Our preferred candidates were lactic, maleic, and tartaric acids. As for the lixiviants, that is the inorganic lixiviants, the suitable candidates for use would be hydrochloric acid, nitric acid, phosphoric acid, and sulfuric acid. And then we saw that using less than 2.5 molar sulfuric acid would actually be a preferred condition. Examples of available oxidizing conditions are anodic oxidation and air oxidation. And then we chose air oxidation under atmospheric conditions to be a preferred condition. This is our selecting leaching schematic. And we see that we have the gray spheres representing the cobalt binder metal, and the blue spheres are representing the tungsten monocarbide grains. When cemented carbide is exposed to leaching media, what will happen is the cobalt binder actually would dissolve, leaving the leaving the tungsten monocarbide grains intact. This is our process flow sheet, showing us the cemented carbide material, which undergoes leaching, and then we have a recovery of the tungsten monocarbide on my left there, followed by the next stage where we have a regeneration of the organic acid, and then the recovery of a cobalt metal, ending up with a recovery of tungsten by precipitation. The following are our preliminary results for this work and discussion. In my top left-hand corner there, we see the cemented carbide microstructure. The dark patches are basically cobalt phase, and then the grains is a tungsten monocarbide grains. On my right-hand side, this is the chemical composition of the cemented carbide, showing us 85.95% tungsten, and 5.28% cobalt, and 8.77% carbon. We looked at the effect of leaching media on cemented carbide, and before me here is the cobalt and tungsten dissolution as a function of leaching media. We see here that actually cobalt dissolution was favored more in acidic media rather than in alkaline media. And tungsten was favored more in alkaline media than in acidic media. We further looked at the effect of parameters. On my left-hand side there, we see the cobalt and tungsten dissolution as a function of acid concentration. From the figure, we can see that cobalt dissolution actually increased with the increase in acid concentration up to a maximum extraction at 1 molar sulfuric acid. Then the figure on my right here shows cobalt and tungsten dissolution as a function of temperature. And cobalt extraction increased with increasing temperature up to a maximum somewhere between 75 and 85 degrees centigrade. On my left is cobalt and tungsten dissolution as a function of solid to liquid ratio. And we see that our good ratio was actually at 1 to 10. And on my right-hand side here is cobalt and tungsten dissolution as a function of time. And from this graph, we see that we actually managed to extract 99.6% cobalt in 10.5 days. We further see here that there was also a co-extraction of tungsten of up to about 10% within the same leaching period. We continue to look at other factors, like we compared actually the performance of organic acids against inorganic acid leaching. The diagram on my left shows the comparison of 3 organic acids, and lactic acid performed better than the other acids. Then on my right, a comparison of inorganic and organic acids. Inorganic acids performed much better than the organic acids. Our conclusions therefore are that cobalt extraction is favored more in acidic media, and cobalt extraction using sulfuric acid, we are able to extract 99.6% in 10.5 days. Inorganic acids achieved better cobalt extraction than organic acids. Lactic acid performed better metal complexation and extraction than maleic and tartaric acid. Our way forward basically is further investigation is underway to optimize the process, derive process kinetics, and also establish controlling reaction mechanisms, as well as determine associated material properties. Our acknowledgements are due to these organizations for their financial contribution. These are our references. Thank you.
Thank you very much for a nice presentation to start off with. Are there any questions? One at the back.
Hello, Alan. Thank you very much for a very nice presentation. Just a quick question. Just moving forward, you had basically tungsten carbide and cobalt in your setup. If you have a complex structure where you've got tungsten carbide with chromium carbide, tungsten carbide, niobium carbide, or tungsten carbide, titanium carbide, cobalt, those sort of 3-phase or 4-phase structures, which is typically what is used in the industry. Do you foresee this as a possible challenge with the methods that you just presented to us right now?
Well, the material that we are looking at actually is what you call the straight carbide or machine-grade carbide, which is basically tungsten monocarbide bound by the cobalt binder. With that, this is what we are able to see. But if we throw in a few more metals, I don't know what to expect. But this actually gives us some hope that probably there could be a way forward.
One question here.
Yeah. On your slide, you're showing lactic acid is better than the other 2.
Yes.
Concentration effects, because are you working with the same concentrations of the acids?
Actually, in order to compare them properly, the concentrations were basically the same. Of course, they are varied, as you can see, but we were working within the same range of concentrations.
And so why is lactic acid the best?
Lactic acid, from what I've seen in literature, actually, lactic acid appears to be the best because it has got a smaller structure, molecular structure, compared to the maleic and tartaric acid. And so it dissociates much easily, dissolves better.
Okay, any more questions? Okay, we can thank our speaker once again. The next focus area to be presented is diamond thin hard films and related materials, and the focus area coordinator, Professor Mervyn Naidu, is going to introduce it.
Morning, everybody. While we're waiting for the slides to come up, my friend Giovanni said I must do a Bollywood thing while I'm up here. So I said I'll do it if he does the curl part. But we're not going to do that. All right, so let me just briefly introduce you to a focus area which is called diamond thinner films and related materials. And I always, when I introduce this focus area, I have to say that diamond is the mother of all hard materials, right? So one of the things that we focus on in terms of research is particularly the properties of diamond and its application in industry, in optoelectronics and electronics. So that's a rather large, broad area for the application of diamond, apart from its, of course, aesthetic value, which we appreciate from a cosmetic point of view, which we don't really focus on at all. Let's just say from a physics point of view. So people within the focus area, apart from myself, you can see the names there. I always mention, of course, one of the original founders of the Center of Excellence, Professor Cummins, who's still very much an active part of our research program, as well as Professor Derry, who's here with us today as well, and Professor Tom Nam, whose work has been pioneering in terms of the application of diamond as a dosimeter for radiation monitoring. So, just move to the next slide, and I'm forgetting I need to do this thing. All right, so just in terms of students that we have at present, we have 3 PhD students and a number of MSc students. Some of them have graduated, you can see we have a couple of students have graduated and some that are present under review at present, which is good. And I'll introduce you to one student in particular a bit later on, who's going to be giving us his presentation for this focus area. So much of the research that we do, like I said, is basically work, how do we apply diamond outside of the cosmetic applications. And one of the big areas, like I said, is the application of diamond in terms of radiation monitoring. The reason why you want to use diamond, for those of you who may not be too aware of its properties, it's effectively tissue equivalent. So if you want to measure doses in terms of what we call medical, it's a medical term for measuring how much radiation you absorb, you want to have a material that responds much like how the body responds. And carbon is that. So there's a very tissue equivalent response in terms of the way the material behaves. So when you measure dosage using diamond, you're effectively measuring how much energy the human body absorbs in the same. It's a very, very close correlation in terms of the material, which is essentially saying the body is made up of like elements, and carbon is one of them. So Tom Nam is the person who's been working on this book, so I just picked up on this. And there's some newer stuff that he's basically working on, which is very exciting, and we'd like to see where this goes. One of the things that we've always been interested in is the properties of diamond from a natural point of view, and its geosynthesis. So understanding defects in diamond, the imperfections itself, is key to where diamonds are formed, how they were formed, how defects are generated. It tells you much about the geosynthesis of the Earth. And one of the outstanding problems that, and just to say something about this particular project, in about 3 years in the making, in eventually producing a paper in Nature, but lots of measurements done, and eventually a group from South Africa, a group from Oxford, and a group from the Max Planck Institute in Germany got together and produced what we think is a solution as to the nature and the structure of the platelet defect in diamond, which is using what we call atomic resolution microscopy. So very kind of proud for that in terms of that achievement. It takes a long, long time. So I always say to students, if you've got a project that looks like it can go somewhere, don't necessarily produce. What we did is we did lots of measurements, but we presented the information in small pieces at conferences and we got people's interest. And eventually collated all of it together into one huge publication, and this is what eventually happens. So don't do too much in a rush sometimes to publish. Be patient about that as well. Other aspects is variation in the damage in diamonds, also very, very interesting part of our research, purely to understand how does diamond change when you irradiate it. How do you recover in structure? Purely to understand something about doping. The other aspect we want to understand is how to alter the elastic properties of an sp3 bonded structure by creating sp2 bonded structures inside. And ion radiation is one of the things, and this is some of the first papers that we produced, understanding the elastic properties of damaged diamond, etc. All right, so very, very quickly now, just if I give over to the student, we're also very interested in collaboration with industry. That's because effectively how associated with element 6 has got to do with the production of what we call this material, which is polycrystalline diamond complex, or PDC. It's something you have a polycrystalline diamond. Is there a laser pointer here? Ah, there it is. You have a polycrystalline diamond which is sintered onto a tungsten carbide cobalt, which you just heard just now about the properties of tungsten carbide. You understand this is a very useful material which polycrystalline diamond can be sintered and form what is called a polycrystalline diamond complex, which is used in the drilling and industry. It's a cutting tool used in the mining industry. It's very useful, and we want to basically understand fatigue type processes in polycrystalline diamond, as well as from physics point of view, the magnetic and signatures of this material. If you can use magnetic signatures to understand something about the wear processes as well. So, effectively, other highlights, you can just quickly read through. We're very happy that we can support and especially form collaborations with other universities and across disciplines within science and engineering. And we try to establish and push that forum all of the time. Being experimentalists mostly, we are able to do that and have access to equipment, especially within the national facilities of South Africa. We use that quite often, especially the Tampa labs. And we've been able to produce a fair amount of peer-reviewed and conference output this year, which we're very pleased with, and we hope that our students continue to assist us in this process, because they're the key to what we do, effectively. Students are what we're about, and producing people at the end of the day. All right, so our presentation today is going to be given by a student who is supervised by Professor Derry and Gordon Maduku from the Gamma Labs. And he's going to be talking about the conversion of hexagonal boron nitride to cubic boron nitride, which is basically taking a soft material and converting it into hard material using ion radiation. So I'm going to give over to Mr. Lisema. Thank you very much.
I'm going to talk about the properties of cubic boron nitride nanoparticles formed by ion implantation. Good morning, ladies and gentlemen. My name is Neutron Diffraction. My supervisor, Professor T. Derry, co-supervisor, Dr. Morgan from Apl Labs. This is just a brief outline. I'm going to take you through an introduction where I tell you about the foundation of my research, why am I doing it, and the possible outcomes. Also explain to you what are ion-solid interactions and the fundamentals of these interactions. Talk to you about boron nitride, take you through my experimental methods, and discuss my results, conclude on my findings. The hardest material known is diamond, right? But this answer can be oversimplified because hardness and strength are not single properties. A material can be strong in one way and weak in the other way. Some materials can resist scratching better, and other materials can absorb force better. And we can also synthesize materials that combine a lot of these properties. Diamond has been used for many years and for many applications.
And the idea of synthesizing a material that is much harder than diamond has caught the community of material science. But research shows that if you want to synthesize a stable material, which is much harder than diamond, it becomes a problem. So now the focus is rather synthesize materials that have the same phase as diamond, but better properties. Cubic boron nitride is the second hardest material known, which has better properties than diamond. Research done by Emily Rabi and Ronald Mashaka shows that if you irradiate the surface layer of hexagonal boron nitride, you can induce cubic boron nitride nanoparticles. The problem that we have is that we have not established parameters that induce this phase change, and we have not determined the properties. This is where I come in. I'm going to determine the effects of radiation in hexagonal boron nitride using ion implantation, establish the parameters that induce this phase change, and also determine the properties. Ion-solid interactions is the field of material science where we accelerate particles with high energies on the sample surface. Radiation can be emitted from the sample and particles can be emitted, and different characterization techniques can be used to analyze the emitted radiation of particles so that you can study the properties of your sample. Cubic boron nitride has two stable structures, hexagonal boron nitride and cubic. Boron nitride has two stable structures, hexagonal boron nitride and cubic boron nitride. A hot-pressed polycrystalline hexagonal boron nitride was used in this experiment. It was cut into 2 mm thick slices using a diamond wire saw located at the School of Physics, which is an excellent piece of equipment if you want to cut thick slices. Ion implantation measurements were carried out using the Varian ion implanter located at Itemba Labs. The ions that were used for implantation was helium, lithium, neon, and boron. Basic implantations were done at room temperature. And the other sets of implantations, they were done at 150 and 300 degrees. This is the sample before and after implantation. The darker region of my sample shows that the sample has more fluence on it, and the lighter region of my sample shows that the sample has lesser fluence on it. Yeah. So after implanting my sample, I wanted to check how does the hardness vary when I change the fluence. So I used the micro hardness tester located in the School of Mechanical Engineering. The load was 100 grams and for 10 seconds. Raman spectroscopy was used to analyze the samples so that we can check if there are any ion-induced phase changes. And these measurements were done at room temperature using the argon laser of 540 nanometers. XRD measurements were done so that we can study the crystal structure of our sample and the atomic spacing in our sample. The plate spacing equation for hexagonal crystal structures, I use this equation so that I can determine the lattice parameters of my samples before and after implantation. The radiation damage profile that is here shows that if I implant with heavy ions on my samples, I cause more damage, but these samples do not penetrate deep, but these ions do not penetrate deep into the material, but the light ions penetrate much deeper into the sample, but cause less damage. This is a Raman spectrum of the unimplanted boron nitride. It has one characterization peak located at 1367 per centimeter. The Raman spectrums that you see here, implantations were done at room temperature. This one was implanted with helium ions, and this one was implanted with neon ions. After implantation, we observed this peak. This peak is a characterization of cubic boron nanoparticles. And then we also notice that after we've implanted our sample, the intensity decreases as we increase the fluence. This is another confirmation that there is radiation damage on our sample. And we also have an optimum fluence here and an optimum fluence at 4 times 10 to the power 15, 6 times 10 to the power 15. This is the same work this is similar work that was done by Emilian Radi, where she used boron to implant her samples, and this side she used helium to implant her samples. We also observed that peak again around that region. Another confirmation that we do have cubic boron nanocrystals on our samples. After doing that, I wanted to check if there's any surface hardness change. So, by increasing the fluence, we do notice there's an optimum hardness value. When we increase the fluence, the hardness do increase, but it reaches an optimum value where the hardness wants to drop. So, I made a table for optimum fluences that you get for indentation and the optimum fluences that you get on Raman spectroscope. These fluences here are the fluences where you get your maximum hardness on indentation. And these are the ones that we established from Raman spectroscope. I took my experiment a little bit further where I wanted to vary the temperature using the same fluence. So I realized that I get more or less the same results where the heavy ions, boron and neon, give maximum hardness. But if you look at this neon peak, when I increase the temperature, the hardness decreases and the boron has maximum hardness. If you come to this spectrum, boron has maximum hardness. This could be that while we are implanting on our surface and increasing temperature, it's like we are fixing the damage. We are annealing the surface and we are also damaging it. That could be one of the reasons why we are observing things like that. So I plotted the stress and strain graphs, which is a nice plot. I just chose this randomly, the 150 implants. Okay, let me just go to these tables. Here, I just want to focus on this. I just call this the threshold stress. And the Young modulus, you get it on the gradient of the graphs from the stress and strain. If you look at this stress is the stress that you need to apply on the surface of the material for you to get the strain. So if you apply anything below that, there won't be any strain on the surface. So this is the stress that I got, and this is the Young modulus. So when we increase the temperature, that threshold stress decreases. It goes to that point when I say, when we do damage to the surface, it's like we are annealing the surface also. We can also check this, the 300 temperature implants. That stress is decreasing. So we did the XRD measurements. This is the XRD spectrum that we got. After implantation, we noticed 2 unidentified peaks here and there. And those peaks appear onto all the spectrums where we implanted with different ions. That's the peak here, that's the peak. So when I look these peaks up in literature, they show that this peak can be a characteristic peak for silicon, meaning that the sample holder that they used to mount my sample on while they were doing the XRD measurements, this could be the silicon peak. And this peak here is the 1,1 peak for cubic boron nitride. So from those spectrums and from that equation that I showed you earlier, I used that to calculate the latest parameters of my samples before and after implantation. And I compared them to the literature values, which they were more or less on spot. And after implantation, you can see that the latest parameters have increased in value. So since when you know what the latest parameters are, you can use that to calculate the volume per unit cell and determine the density of your material. These are the values of the densities that I determine, and I also determine the atomic radius in the samples, which again, they are more the same like the ones that I found on literature. Then I established the relationship between the atomic radius and the density, which shows that if the density decreases, the atomic radius of your sample, if the density increases, the atomic radius of your sample decreases. So in conclusion, the simulation shows that heavier ions have shorter ranges as expected. Raman signal for crystal cubic boron nitride has 2 vibrational modes at these 2 peaks. Increasing fluence decreases the intensity, evidence that there is radiation damage. After implantation, we observe a broad peak at that. Literature shows that cubic boron nanoparticles tend to show that peak. Heavier ions have a higher hardness value. The peaks that were not identified on the XRD spectrum is the 1,1 peak for cubic boron nitride nanoparticles. And this peak that was identified at this angle is the 311 diffraction peak for silicon. The latest parameters was calculated and compared to literature, and the density and atomic radius relationship was determined. These are my references. I would like to thank the Center of Excellence for giving me this opportunity and for funding my research. Thank you.
Thank you very much. Very good presentation. Are there any questions?
Maybe just this question here. Is there a temperature above which the cubic boron nitride particles will anneal back to the hexagonal form?
They will anneal back to the... I don't know, I'm not sure about that one. But what I know is like, the more we increase the temperature, the hardness of our sample, the more we increase, let me just go to this. The more we increase the temperature, the hardness of our sample decreases as compared to the implantations that we did.
This is what made me think of maybe something situ self-annealing process.
Yeah.
And therefore even the energy imparted by the beam will play a role. I just mentioned that for you.
Yeah, something that I think I should look at it. But yeah, thank you. Yeah, something that I should look at.
Remember, the cubic form is the stable form.
So it won't anneal back.
It won't anneal back.
Okay, that's what I wanted to know.
Okay. Are there any more questions? In that case, I've got one. How reproducible is ion implantation?
Can you rephrase your question?
How reproducible is ion implantation? I.e., is it very easy to get the same results if you do it on different days?
With regards to the results that I got, yeah, I do get similar results. It doesn't depend, like it doesn't matter which day did I do my experiments, I do get the same results.
I was being excited.
Yeah, I do get the same results.
What other things could affect it?
Could affect what, the hardness of my sample?
No, your ion implantation.
Or what other things? The other things that could affect it is like, it depends what parameters are you using. Changing the energy can affect that. And also changing the ions can affect that.
Okay.
Yeah.
Thank you very much.
Thank you.
Right, any more questions? If not, we thank our speaker again. Oh, hang on.
There's one behind you.
Ah, yes.
Your ions that you implanted on your sample, is there any reason you chose the ions?
Yeah, the reason why I chose those ions is because there were studies done by those ions. And the only ion that I just added there is neon, because I just wanted to check how will this noble gas affect into my sample. Yeah.
And one more.
One quick question. You mentioned in your conclusions that 2 modes that are observed for cubic boron nitride which is the transverse optical and
Yes,
the
yes.
longitudinal optical.
Yes.
You only saw the longitudinal optical.
Yeah, I only saw the
Why
longitudinal.
don't you see the translational transverse optical mode because of the vibrations emission from Raman?
Because what I've read on literature is that cubic boron nanoscale particles, because here is for single crystal cubic boron nitride. So for nanoscale particles, you only observe this peak. Okay.
Okay, I think we must let our poor speaker off the hook. Thank you, The next focus area to be presented is new ultra-hard materials, and Professor Alex Pont, the focus area coordinator, is going to introduce it.
Okay, welcome everybody. So, as every year, new ultra-hard material has to be presented, and as you know, it's a mixed bag. So many of different things are collected under the new ultra-hard material focus area, and I think that would be a nice mascot for. Okay, so it's not much change in the people that make up the focus area. I mean, the most notable change is that Robert Warmbier just switched side, and he's now at UJ. Other than that, more or less the same crew like every year. And just to summarize some of things that were happening. So publications were certainly up. You see a lot of regular publications, but also conference papers, and 3 book chapters, one about glass ceramics based on sol gel, and 2 chapters about computational plasmonics. So we were quite active there. And the other stuff which is noticeable, and I thought actually Natasha would mention it, but she's very modest, is basically we more or less made a report for the government about energy efficiency, and 3 people from the COE actually working on that report, so it will be launched in May. We have almost no MSc students anymore, a lot of PhD students, and I said PhD, they're still MSc students, but they're about to submit very soon, and then basically take up PhD. So that's how a focus area looks like, so we have to take some measures of taking up MSc students again to get some blood into the focus area. So from the outreach, and this is something I want to show you, so we were also very active in just going out and go to the wider public and show some of the stuff we are doing here in the COE, especially also in combination with renewable energy. So here you see some of the students here in the audience. So they went to Venda and they were talking to school children, and they get in touch with solar cells, with batteries and other stuff. So thanks to all the students who did a great job there. I think they also had a lot of fun. And I attached a report that the students wrote to the annual report of the COE, so you can read them and see what they were doing there in detail. Okay, as for merge, well, the big bilateral project with Italy came to an end. Unfortunately, it was a lot of money, a lot of support from the Italian government. It looks like they were very, very happy with our final report, so they gave us some money to write a book and get us some international experts to write something about new types of solar cells that we and others are trying to develop worldwide. So, as you see, this is, for example, the last workshop was in Rome, and so several people from the COE basically gave talks on the conference on rare earth ions. We presented our work on solar cells and a poster, so it shows that actually we are very well embedded with our colleagues worldwide. So other things that we do, we saw the tungsten carbides. So what we do in our focus area, for example, we examine this kind of stuff with local probes like Merz power. So this is one of the things that we do. With the rare earth ions, it's very nice. So we not only model them in terms of solid solar cells, but we also have somebody who really can measure all that stuff and all the difficult things that happen in the environment of the rare earth ions, which is very complicated. So that comes in very handy for us. Well, Dave Peening, that's his favorite materials, that's one of them. This is the solid electrolytes. And I just mentioned that because now we have Kenneth Otsuemena as a new member of the COE, and Dave is one of his main collaborators here, especially concerning battery supercapacitors and other stuff. Yeah, another good news is, and here I give all the credentials to Robert, is we finally found that damn plasmon, terahertz plasmon in graphene, also theoretically and numerically, which was a big issue. And it was only possible due to some very subtle changes in the algorithms, and it's all Robert's work. My contribution was bitching and mourning all the time. We didn't have any clear results there. Okay, and then finally, and that is the introduction to the talk that we're going to see in Gio's group. They do some very interesting stuff. They look at the interlinking between carbon nanotubes. And if you follow a little bit the literature, then now there's the news thing coming up, magnetism in amorphous carbon materials. That's the new thing. So, and especially this kind of bondings are playing an extremely important role. So I think this is very important stuff that's done in Gio's group. And you can see with Raman, you have a good idea actually what's going on locally. So that brings me to the speaker, and that's Mr. Liberty Capesi, and he will talk exactly about that problem. And so without much further ado, the stage is his, and hopefully we look forward to a very nice talk. Thank you.
Good morning, everybody. Thank you, Professor Alex, for the introduction. I'm going to talk about probing for carbon nanotube interlinking after ion implantation and pressurization. My talk is going to start with a brief introduction to the system that we're dealing with, followed by the motivation behind the work, and we'll then look at some interesting results, which is going to be followed by our conclusions from this work. Maybe to start with, let's look at what we are talking about today. It all starts with the graphene sheet, which is basically a network of hexagonal systems of carbons. It's shown on the left panel here. Depending on what you do, you can roll up that graphene sheet into a seamless tube, and you can end up with 3 different classes of carbon nanotubes. We also have different types of carbon nanotubes. For example, what I mean to say is you can have one seamless tube that's then a single walled carbon nanotube, or you can have two concentric tubes and you then end up with a double walled carbon nanotube as shown on this picture here, which is an HRTM image of a bundle of double walled carbon nanotubes. Or you can have, well, several concentric tubes that then gives you what we call a multi-walled carbon nanotube. What's interesting to us are the mechanical properties observed on an isolated tube, which are very remarkable. For example, we have shown here the experimentally measured tensile strength. As you move from an isolated multi-walled carbon nanotube and you go on to systems of bundled carbon nanotubes. Now we do have drastic changes or decreases in the mechanical properties when you move to bundled systems, which is as opposed to what you would expect, because you have, we should get an enhancement at least. So we are trying to promote the interlinking on the individual's carbon nanotubes, probably to get enhanced properties when you are now looking at the macro system of carbon nanotubes. And yet we do have these carbon systems having one of the lowest densities, which then means that we have the carbon nanotubes being pretty good candidates for very strong, lightweight materials, for example, for aerospace engineering. So our major goal is to try and promote the interlinking, and we are using two different parameters, that is ion implantation. We are using implantation to just introduce some nucleation sites into the system, which we hope that at the end of the day, after pressurization, we then introduce the interwall or intertube bonding. We know already that high pressure decreases the energy barriers to sp3 conformation. So our major goal is to try and maintain those properties that are measured on an isolated tube when we now move to a macro system consisting of bundles or aligned carbon nanotubes. As a result, we used implantation. We also used high pressure techniques, and our major probing technique was Raman spectroscopy. And we used a WITEC system which consisted of a confocal Raman spectrometer, and we tried to limit the damage to, the carbon nanotubes by making sure that we used a low laser power. We realized that it was necessary to divide the area, the sample area, into individual regions or areas of 10 microns by 10 microns in area, so that we could probe inside each of those areas to get 16 spectra, for example. We had a 4x4 grid in each of the 4 areas. Then at the end of the day, we then had 64 spectra for each pressure used, so that we could have a global representative of the spectrum. We'll realize why we had to do that later on. Our major focus was on 3 individual Raman signatures of the carbon nanotubes, namely the D band, which arises from any asymmetry in the system. We also have the tangential vibrations giving rise to the G band, and we have the radial vibration of the atoms in phase, which then gives us the radial breathing modes, which at the end of the day gives you the picture that the carbon nanotubes is as if it's breathing. Our major focus was on individual spectral parameters, for example, the line width, the intensity ratios, the area ratios, and we have shown here the spectra collected from different spots on the starting material, showing here the inhomogeneity issues. We have normalized the data here to the G-band so that we could make intercomparisons between the spectra. We have significant changes when you move from one spot to the other, so that then prompted us to use averaging. It's well known we can create nucleation sites using implantation, but we were trying to maintain the mechanical properties, so we tried to limit the damage to the system by using light ions as well as using low to medium fluencies. But we also wanted the ions to penetrate deeper into the system, so we had to use moderately high energies to achieve that. Our major high pressure tool was what we call the diamond end-view pressure cell, which is a system or a tool that consists of two diamonds facing each other. In between those two diamonds, you then have a metal strip or metal gasket, at the center of which you then drill a hole that then acts as your sample cavity. We have an example here shown on the left side. We used, we also included rubies into these sample cavities so that we could excite the ruby, and the wavelength shifts in the ruby fluorescence lines then enabled us to determine the pressure. Results, we had two samples, a starting or reference sample with no implantation, which we then pressurized to high pressures, 30 GPa. Then we had to implant another sample from the same batch, and we also pressurized it to 20 GPa. What's shown here are the spectral, or the evolution of the spectra from ambient pressure to the highest pressure probed, which is 20 GPa. What's of interest to us are the changes that are happening to the major Raman signatures, that is the D2 as well as the G. We have the expected shifting in the positions or characteristic of phonon hardening. You're reducing the unit cells, you're increasing the force constants, and as a result, you expect phonon hardening. We do have, of course, the influence of the first order diamond end-view peak, which is not a major issue as you increase the pressure, because the D-band then shifts from underneath the diamond first order peak. What is interesting to note from here are the relationship between the relative parameters of the D to the G. We went on to extract the parameters from this data so that we could make intercomparisons between implantation and the sample with no implantation. For example, we have the position shifting following what's expected from phonon hardening. But what's more interesting from this slide is the changes that are happening to the position of the G-band as you increase the pressure, especially for the implanted sample. It does not follow a typical phonon hardening trend, mainly because it's well established that the G-band decreases as you increase, or as you start to have sp3 bond formation into in your system. But in this case, we don't have a drastic decrease as expected. We just have a change in the pressure dependencies to lower values, because we have two mechanisms that are competing with each other. We have phonon hardening, then we also have the onset and proliferation of sp3 bonds in the system, and hence we then end up with the trend shown here.
5 minutes.
And what's more interesting to us are the intensity ratios between the D to the G and comparing the implanted sample and non-implanted sample. The non-implanted sample simply or generally increases, then it tends to saturate at around 65% D to G ratios. But the implanted sample follows a very interesting trend, which is in line with what has been established already with the, from the effects of increases in the sp3 volume fractions in the system. We have, for example, the step number one. We also have step number two, from which we can then conclude that we can estimate the sp3 bond formation to be about 10% because we have a 90% ID to IG ratio, which then translates to about 10% volume fraction of sp3 bond in the system. We wanted to estimate the average distances between the defects introduced into the system, and we have a trend which is in agreement with the previous slide because we have the distances being extracted from the intensity ratios. We estimate from this trend here the optimum or the average distance between the defects to be 2.2 nanometers at a low pressure of about 2.5 to 3 GPa, which becomes our minimum tailored pressure to introduce the sp3 bonds into the system. Now we recovered these samples from high pressure, and we have now shown here the intercomparisons and the changes that are happening to the samples. Starting with the non-implanted sample, starting double nanotubes, and we see the effects of increasing some defects or introducing some defects by looking at the, for example, the red curve, which is the implanted sample before pressurization. All the spectra here have been normalized to the G so that we can also make intercomparisons. Now, what's interesting from this slide is the enhancement in the D to G ratios when you look at the sample on that had both implantation and high pressures. We have significant increases in the areas as well as the intensity ratios. We went on to look at what's happening now to the radial breathing modes. Do we still have the signatures? And what we have shown here is that we still have the radial breathing modes, which then means that we have maintained or we have preserved the integrity of the carbon nanotubes, which means we still have this scenario here. Our conclusions are that we have significantly increased the D to G parameter ratios, and we have estimated the sp3 volume fraction to be about 10% in the system, and the minimum tailored pressure for such volume fraction is about 2.5 GPAs. We wish to continue to further characterization techniques, and we also wish to introduce laser heating so that we can decrease or we can facilitate the bonding kinetics. We also wish to move on to boron nitride nanotubes. And with this, I would like to thank the following people and institutions, in particular the Center of Excellence, for their funding for this study. Thank you.
Thank you very much for another really nice presentation. Are there any questions? Yes.
Could you just, maybe for my sake and everybody else's, tell us how you prepare the material for implantation and how you take it and put it into the Raman and cell, because the volumes of material you have to work with are very different from the one stage to the next stage.
Okay. We had some things to consider. For example, we had to look at the probing depths of the Raman. We also had to look at the implantation depths. So as such, we had to first pressurize the sample so that we could try and have maybe a flat enough surface. That then would enable us to, what can I say, cater for the implantation depths for Raman as well as, for the probing depths for Raman as well as the implantation depths. So we had to pre-indent, to pre-pressurize the sample up to about 4 GPa. Then we went on to do the implantation. So we put the sample in the sample cavity, we pressurize it a little bit, we take it out of the diamond NMU cell, put it into the implanter, we do implantation, then we start the pressurization measurements. Yeah. The major issue was on probing depths.
Okay, any more? To sort of follow on from that question, what volumes are you looking at? Because I know when you do your diamond envelope thing, that's very, very small.
The starting diameter of the sample cavity was 250 microns. That is 0.25 millimeters.
Right.
It's not easy to work with such a lot. So yeah, we started with 0.25 millimeters.
Yeah.
Then when you pressurize, we expect a decrease in the sample cavity, of course, which then goes to about 180 microns.
Okay, no more questions. Yes, one more.
So one short question. So I always need a picture of what's going on under high pressure. So when you put the carbon nanotubes under high pressure, so this change in the local binding from sp2 to sp3, is it just because you cram everything together, or is there also shearing involved?
These are very high pressures, which means as you increase the pressure, you expect overlapping in the electron densities. For example, you can enhance, we can break some bonds, introduce new bonds. But with high pressure only, what has been observed is, as long as you're working within appropriate pressure levels, well, everything can be reversed back to what you started with, which is why we had to introduce implantation into the system. So,
Okay, one more question.
Can you comment on the purity of your starting materials and source and possible coverage? Because in your multi-wall carbon nanotube example, it's not sort of amorphous material on the surface. Was there any on your double-wall nanotubes? Can you comment on that?
yeah, we foresaw the issue with, a number of hindrances, so we had to just purchase commercial carbon nanotubes. We realized that we were going to take too much time. This work was done during the period that I was doing my master's. So to limit on the time frames, we had to purchase these samples. They had a 10% metal oxide impurity level with an average diameter of about 3.5 nanometers. Yeah.
You use them as such?
Sorry?
You use them as they were?
We used them as they were. When we realized the homogeneity issue, we thought of other things like, for example, annealing the sample, maybe to improve on the purity. That did not work. We went on to try the mapping or averaging out. So we used them as purchased.
Great. Any more? No? We can thank our speaker for a very nice presentation. Right, it's nearly tea time, but not quite. So what we're going to do is we're going to have a group photograph for all the students and staff. And do we want to get in the middle bit? If we can all get in the middle bit, if we can push the microphones down, so it doesn't look like somebody's got one growing out the top of their head or through their ear or whatever, and get in the middle, please. And we will be going live again at 11 o'clock. So the sooner we can get in the middle and have our photograph, the sooner we can go and have some tea.
it here.
Cheese. That wasn't very enthusiastic. Tea time.
Tea time.
Thanks, guys.
Thank you, Casey.
Break time.
It's in about 15 minutes when I come and set up my stand. I'm presenting.
Presenting present.
Oh well, I'm
Okay,
the student presentation, so Leslie will introduce me and then.
That's great.
Yes. People can watch us at tea. But let me maybe see.
No, it's about you make it. Thanks.
So no one is the young speaker.
It's on the way. This is how you get the money. Okay? This is how you get
I'm running back to my cave.
Oh no! How you can negotiate this thing. No, you want to stick with it. That's fine. Yeah, but there's also
I've restarted my process.
Budget around 5. I'll Wish you all the best. Yes. Good morning.
Do I need to turn this thing on? Is there like different stages of on? Is it this button? No. Press and hold. Press and hold? Okay. Press and hold. Off. That's it. Okay. Cool. All right.
It's not possible to be the greatest.
I'll just stand here.
Okay. Delineation. Again, have shown, and then when you change slide, the next slide is on the
When they look at the size, they have different slides. You see that? Okay. The only problem is doing two things.
Okay, that's a bit of
Is it not possible to... Oh, you want to stream two things at once, that is awesome. But I mean, what happens if you have the lens, I mean, what if the window is the screen and the person? Is it a bit difficult to focus on both at once? I guess they're completely different lights.
it's a bit glitchy. Oh, the greatest.
What if it's slightly that side? Like that, so like you can see the top of those people on the slides a little bit. But you'll know more about this than me.
Yeah, it's still being on that side. But the thing is, can we...
Oh, I see what you're doing.
Hello.
How are you?
Okay, and you?
Yeah,
You ready
you.
for this, eh?
I think so.
Well, yeah. Can I not put pressure on you? You know, SMA's won it for the last 2 years. Eh?
Oh, really? Oh, dear, no pressure. And it was one of Prof. Alesso's students who won it 2 years ago as well, so there's additional pressure there.
3 years ago.
There was Dean for Atmosphere.
Oh, Dean, yes. Yeah, no, listen, no pressure. Yeah, so you know there's no pressure.
Yeah.
I've been very careful in selections over the last 3 years.
Oh, really? In selecting who presents and...
Because, it's competitive between the focus areas.
Yeah, I guess it's got to be.
It's a bit of a, it's a bit of a...
My fear is that I've tried to put in too much. I guess that's it.
Well, no, that's a normal thing. So don't try and rush it. And if there's something, if you think that it's going to be too long, when she says 5 minutes, just gauge it, and you don't have to say everything about every slide.
Yeah.
You can just highlight some things on the slide.
You know that you're live, right?
Am I live? Okay, I'm coaching.
Is there a microphone around?
There is.
Thank you.
You need to come here.
It's well aligned with my slides because I have quite a large
One.
thing on the top left has like a logo, so you don't really need to see the top.
Hey, you missed it.
No, you don't have time to shoot. No, hang on. The problem with those stipulated mics is facial.
It would be nice to continue chatting outside, but our feed is live, so that's why we would just like to get back on, streaming.
I can't do anything. I haven't introduced you yet.
Oh, right, you're introducing.
Carry on. Oh.
Okay, I've been told to just introduce myself.
Okay.
Okay.
Right. Okay. Start again. Professor Leslie Chow, who's one of the focus area coordinators for the strong metallic alloy, she's going to introduce her focus area. So now she can carry on with it.
Good morning, everyone. And yes, so I just want to give a bit of a background as to what we are about. As you can see, Mintech is has quite a big role to play in our focus area. They're the only non-VITS focus area coordinator in the COE. And so I shared this role with, in 2017, up to 2017 with Dr. Jones Popple. And from, I think it started already, we now have Dr. Alan Mwamba, who is going to be the focus area coordinator. But I do a lot of the in-house work on the VITS side. So just who we are. These are the members that we have, that were members in 2017. We have had some other members from other universities in the past and hope to have more members in the future as well. And in 2017 we had 29 students. Okay, so what do we do? Well, we look at metals. And we in general don't look at pure metals, we look at alloys. And so what we're about is developing those alloys and optimizing their processing so that they can perform to the optimum in the environments that they are selected for. So we look at changing the microstructure, and that often gives us the change in properties or the optimum properties that we need. We also are mostly looking at bulk alloys at the moment. So that means, you know, we're not looking at nano anything really. That's up to some of the other focus areas. And in general, we're not looking at thin films or anything like that, but we do look at coatings on bulk materials as well. And so we typically have steels, and not just, you know, the steels that you use to make your fence at home, but some very high performance steels used in the power station, you know, power generation industries, in automotive environments, in highly corrosive environments, that sort of thing. We're also looking at titanium alloys, and this is quite important because, as a lot of you might know, we have I think it's the second largest reserves of titanium in the world. However, we do not do any beneficiation on that. We do produce a lot of pigment for paint with titanium dioxide, but we have a very low percentage of titanium metal that we actually produce in South Africa. So the government has created the Titanium Centre of Competence, and that is to try and produce cheaper titanium metal in South Africa so that we could be internationally competitive. So it's a long process, and we are part of that, so we're hoping to get a lot more work on that in the future as well. And then we also look at some novel alloys, nickel, cobalt, platinum-based alloys. A lot of that work is done with Professor Leslie Cornish, because she's into these funny ternary, quaternary, quaternary. I don't think we've got to hexaternary diagrams because it's a bit hard to see in more than 3 dimensions anyway, you know. And yeah, so we're looking at coatings as well in extreme environments, high temperatures, very corrosive environments. And what's quite a big thing at the moment is a laser shock peening, which is done in collaboration with the African Laser Centre. And a lot of that work sits with Claudio Polisi in mechanical and industrial and aeronautical engineering. And additive manufacturing, as has been mentioned today already, is becoming a really, the whole issue of near net shape or net shape reduction of components so that you don't have wastage, the time, the expense and so on of machining and doing a whole lot of steps. If you can produce your final component in one step from powder, then you have a great advantage over other competitors. Okay, so what happened in 2017? Well, we had 20 MSc and 9 PhD students, of which 12 were females. Go girls! And we've had, if we've looked a little bit ratty over the last while, up till now, we've had about 11 MSc and 4 PhD submissions since October. And so it's suddenly everybody's decided they're submitting at the same time. And we've had 2 approved patents and 2 patents that have been filed, and much more. And at first I was just going to talk about this and not put it on slides, but then I thought, well, it's going to be quite difficult to lay this all out. So Yonela Magwebi won the MSc Charter African Scholarship. She's been awarded one. And then we've got a whole lot of student presentation prizes. They obviously are being competitive among themselves about who's going to be the best presenters. So we're very blessed with that. And we had 2 students that presented proposals for postdoctoral fellowships with AISA RISE in Kenya. And I'm very happy to say that Michael Budanran was awarded a postdoctoral fellowship. So we're just trying to get him to wrap up his PhD at the moment. No pressure on me. And he also presented at the Gordon Research Conference on Physical Metallurgy in the USA earlier this year. He was also in the FameLab finals. He made it to the finals in South Africa, one of 10 people. And what I didn't put up there, I think he was the science, I can't think of science something, also presentations and where you science writing. So he was one of the finalists in that as well. And we had a paper that's been cited quite a few times, so that's been quite nice to have our name out there. Okay, that's it. So there's no pressure on Sean whatsoever. Sean van Staden, who's going to present now, can come forward, so I'm sure, because we've won this for the last 2 years, and I think we've won 3 out of the last 4 years. So, Sean, no pressure at all. Huh?
Thank you very much. Good morning, everybody. My name is Sean van Staden. My supervisor is Prof. Bolese. She had to run out for a lecture just in time. And I'll be talking today about residual stress measurement and parametric analysis of laser shock peening of aluminium alloy 7075. Laser shock peening is a process where we take a material, we cover it in some transparent medium, and we fire a laser. We pulse a high-energy laser at that material. The laser-material interaction causes a plasma to form, and that plasma is trying to expand, but it's confined by that transparent medium, which in turn causes the high pressure to form with that expanding plasma, and that pressure propagates through the material in the form of shock waves, hence the name laser shock peening. That shock tends to plastically deform the material, which in turn, the material response is to set up a compressive residual stress. Now, compressive residual stress is beneficial in that it prevents fatigue, so it can extend the fatigue life of certain components, and therefore it has a lot of application in areas such as aerospace. And in fact, this aeroplane is, they use laser shock peening to form the wings and to improve the fatigue life in some of the components. We want to look at this residual stress profile. So the residual stress profile that's typically induced looks something like this. Everything below the axis is compression, everything above is tension. So we want predominantly to be in compression. And we're interested in improving the surface residual stress, the maximum compressive residual stress, as well as the depth to which the residual stresses are compressive. And we want to look and see how we can improve that by adjusting the LSP process.
In order to measure residual stresses, we need to use a number of complementary techniques. Each of these are quite different. They measure to different depths with different resolutions and have different strengths and weaknesses in terms of time and cost and availability. And we'll look at that in a moment. We use a lot of diffraction techniques, which a lot of the presentations before have spoken about spectroscopy, where diffraction is used to characterize a material, looking at the interplanar spacing based on the position of a diffraction peak. With residual stress measurement, we look at the shifting of the position of that peak, which tells us the strain in the material, which in turn gives us the stress in the material. Laser shock peening can be controlled using a number of parameters. Power intensity, which indicates how much energy is being put in. The spot size, which tells us the size of the spot. And the percentage overlap, which gives us an indication of how many spots there are in a particular area. So the objectives of this work were then first of all, to measure the residual stresses in laser shock peened samples and to compare those results and to critically compare them so as to be able to develop a strategy for parametric analysis, which leads us to objective 2, which was to perform a parametric analysis, have a look at how these different parameters affect the residual stress profile. But more than just the residual stress profile, we're also interested in the surface morphology and how it affects the surface, and also the micro hardness of the material. The selected alloy, aluminium alloy 7075, is quite common in the aerospace industry. We also look at things with different thicknesses because it's quite common in an aircraft structure for it to have different thicknesses and different components depending on the need of that particular component. So we split the project up into 2 phases. Phase 1 looked at objective 1, which was measuring the residual stresses. First we performed laser shock peening. These looked at the stresses in a large depth through the material, and these residual stress measurement methods looked nearer to the surface. The laser shock peening was performed at the National Laser Center at the CSIR in Pretoria. And the sample geometry was that it was 60 by 60 with 4 peen squares, and the thicknesses were 10, 6, 3, and 1.6 millimeters. The peening was performed in a raster pattern, which means that we scan and then step, and scan and then step. This is important because it induces a certain directionality into the results, which we'll see in a moment. All the samples in this case were peened with the same parameters, which are over there. Now, the incremental hole drilling is the most convenient method, so we use it sort of as a base on which we evaluate our other methods through the depth and at the surface. This is because it measures to a fairly good depth of 1 millimeter with quite good resolution as well. It's also available in our labs. It's downstairs from the offices in our lab. It's also relatively cheap and takes about 2 hours to perform a measurement, so that's fairly quick, fairly convenient. The negative sides is that it can be unreliable at times. It's quite easy for a strain gauge to break or for something like that to happen. So that's a downside. It's also a big drawback within the aeronautical industry is that it's limited to samples thicker than 6 millimeters, and our samples are typically thinner than that. So we were also looking at the effect that would have. These are the results for those 4 different thicknesses with the incremental hole drilling. And the trend is that as the thickness decreases, so we have less compression in the sample. This corresponded with an increase in the deforming of the sample, which would decrease the compression at the surface. And so this result made sense. And in addition, we would need to validate it further. So the trend made sense. It's typical of laser shock peening, but we would need to validate it at the surface and through the depth. To validate it through the depth, we first use Neutron Diffraction. Again, this is quite convenient. It's available 50 kilometers from WITS at the Nexa facilities at the Safari 1 nuclear reactor. In this, we use a neutron beam. We diffract a neutron beam through the material and look at the shifting of the peak. Neutrons are able to penetrate more than 100 millimeters of aluminium, so we were able to measure the stresses throughout the whole depth, which is really convenient. However, you need quite a large gauge volume. You need quite a large area. See how big this red square is over here? You're measuring over quite a large area, so that means it can average rather large stresses, and it also tends to be inaccurate at the surface. We also traveled to the argon advanced photon source in Chicago to measure the residual stresses with a synchrotron. The pros of this one is that a lot of the pros are the same as the neutron diffraction, in that it was could measure through the full depth, and in fact it could measure this with a smaller gauge volume. You can see the red rectangle this time is a lot smaller than before, so this was a positive. And what took 2 weeks at Nexa took 1 day here. The downside being that it took a long time to get there, it was expensive to travel. Thank you to the Shelley. And but it was also the other downside, yeah, it's expensive, and it's also a long lead time. It can take 6 months to a year to get beam time at this facility. These are the incremental hole drilling results which we saw a moment ago, and these are the neutron diffraction results, peened and unpeened. We saw a 0 on the unpeened sample, which made sense, and then we saw very good correlation with the incremental hole drilling, except near the surface, which I did anticipate the neutron diffraction to not be accurate near the surface. Interestingly, we see very close correlation with the argon results. This gave us good confidence in all three methods that we were getting this good correlation. And again, there's something different happening at the surface over there. We saw the same trend in both directions. To look at the surface, we used laboratory X-ray diffraction. This again was at Nexa. They've also got a Brooker D8 Discover, which is, it only measures at the surface at about 26 micron, and at an intermediate area, I think it's not too bad. It could be smaller. It's fairly quick. It took 2 hours to do one measurement, so we were able to do quite a few measurements later on in the project. We also traveled to the Electro Synchrotron. This one is able to measure to slightly greater depths than the laboratory X-ray diffraction, but still not as great as some of the other synchrotrons. Here are the results looking at the surface for the 4 different thicknesses. Just note that if you look at the 6mm thick sample, we see the laboratory X-ray diffraction shows a very close correlation with the incremental hole drilling. So whereas neutron diffraction went along here, now we can see with laboratory X-ray diffraction quite a close correlation, a confirmation of that trend near the surface. And so this highlighted the importance of using multiple techniques instead of just one, not only for confidence in the results, but also to validate the results. And also to complement the results, sorry. The electro results also showed a fairly good trend, but interestingly, more so in one direction than in the other, and that was a systematic problem. And the reason for that was because the samples are rolled, and so there was a preferential alignment of the grains, and so we used the same counting time in both directions, so we got it more inaccurate in one direction than in the other. This one is inaccurate in both directions because when we clamped the sample, we clamped it too hard. So this was a lesson learned. Don't clamp the sample such that you increase the stresses inside of it. For phase 2 of the project, we varied the LSP parameters. Then we looked at the residual stresses at the surface, then through the depth. And we also looked at some complementary studies, which I had mentioned. The samples were smaller this time, 28 by 28, and again the laser peening was performed at the National Laser Center. This time, however, we varied the parameters. And we varied them such that we looked at different spot sizes, at different power intensities, and then we also looked at increasing the percentage overlap of the peening treatment to the point where it was saturated, which means that if you increase the percentage overlap past this point, the deformation of the samples stopped increasing. We did the same on thin samples. These samples were 10 millimeters, and the thin samples were 1.6 millimeters thick. We just varied fewer power intensities in this case, because we were more interested in the spot size in this case. The residual stresses were measured with methods I've already described, laboratory X-ray diffraction at the surface, and these 2 methods, incremental hole drilling, and the energy dispersive synchrotron through the depth. We're going to look first just at the surface, because it gives us a good first indication of what's happening and how the parameters are behaving. And because the facility at Nexa was really good, we were able to do the full design of experiments. We were able to analyze the full design of experiments, which we weren't able to do with the other methods. Right, we see that if we look first at power intensity, as we increase power intensity, we get an increased compression. This makes sense. I think we're hitting it harder. Interestingly, when we decrease the spot size, we got an increased compression. So this seemed counterintuitive, but we'll explain more of this in a moment. And as before, if we increase the thickness, we get an increase in the compression. We also saw an increased anisotropy in the results as we increased the power intensity. This is because of that directional nature of the peening. The harder you hit it, the more of an effect that directionality has. Here's the effect of spot size. We see again, consistently as you increase the spot size, so you get a decrease in the compression at the surface. We'll be able to look at more of this when we look at the surface, when we look through the depth. We'll be able to understand that a bit better. We also again saw an increase in power intensity, increased the compression, and again, increasing the thickness increases the compression. This time, as we increased the spot size, we got a decrease in anisotropy, and you can see that for all the samples, they're getting closer. This was because with a larger spot, to achieve the same percentage overlap, because the percentage overlap was kept consistent in both cases, we had fewer spots. And so fewer spots means less directional. I also suspect that that's the reason we're getting a smaller compression near the surface. With a larger spot, that is. Now, effect of saturating the percentage overlap. The important thing is that when we increase the percentage overlap, we get an increased compression at all 4 spot sizes. More so at the larger spot sizes, where the difference in the percentage overlap was greater. We saw the same trend in thin samples, and again, from thin to thick, we get an increase in compression. I'm not going to try and explain the anisotropy on these graphs. They're a bit messy, but we'll come back to that in a moment. Here, now we look at the depth profiles. The depth profiles, here first, a comparison of all the methods to see that our method was all right. And we see close correlation at both a large and a small spot size. Again, this highlights the importance of using multiple techniques because as an example, this one here, with only incremental hole drilling, we wouldn't have been able to see the depth to which the residual stresses were compressive. And so this, and again, the surface, near the surface, we have that difference where it was important to use the laboratory X-ray diffraction. So that was a definite lesson we've learned going forward in how we evaluate our residual stress measurement techniques.
1 minute more.
Thank you. I'll go through it quicker. Increase in power intensity increased the compression right through. Increasing the spot size, as we saw before, decreased at the surface, but it increased drastically the depth to which the residual stresses were compressive, and that was because a smaller spot makes a spherical shock wave which does not penetrate quite as deeply, but a planar shock is able to penetrate more deep, and the larger spots makes more of a planar shock wave. Percentage overlap, we only saw the increase in the compression near the surface, but there was little difference through the depth, and this was the same in a larger spot. Here we can talk about the anisotropy. We can see that for more spots, again, we get an increased anisotropy in the results. The surface roughness was increased for all cases, and the SEM, we were able to see the effect of the raster pattern on the surface, and we were also able to see the effect of melting and resolidification of the surface. This can lead to compressive residual stresses, and it can cause microcracks, so it's important that we evaluate this at different parameters. And then we saw an increase in the micro-hardness. So in conclusion, we learned that we need to measure the residual stresses using multiple techniques. The techniques we used compared well and validated each other and complemented each other very well. We also saw the effect of varying these different parameters, and we were able to evaluate all of them on the residual stresses, the different aspects of the residual stress, as well as the additional studies such as the surface morphology and the micro-hardness. Future work, we're going to put this work into a database which can be used as a benchmark for future studies. You'll see some of the posters outside talking about the finite element modeling of laser shock peening. You also see some on titanium additive manufacturing. A lot of this work has helped to form a basis for that. We also need to look at different things than just the residual stress, such as fatigue life. Another poster outside you'll see is one on looking at corrosion and the effects of laser shock peening on corrosion. And so this work is forming a base for that, all those different works. Big thank you to the Centre of Excellence for funding this Masters. It's been good fun. Thank you to everyone who I worked with at the different facilities. If I'm not mistaken, someone from Nexus here, so thank you very much. And the other guys aren't here, but yes, thank you. Yeah, I'd like to acknowledge Prof. Polese, who's been a great supervisor as well, even though she's not here. Thank you very much.
Thank you very much for a very nice presentation.
Thank you.
Prof. Polese did fill out forms in triplicate to allow her to go early, so that's okay. Are there any questions?
Yeah.
Just one little question. How did you go about getting D0?
Okay, so we didn't have a D0 sample, so what we did was we assumed plane stress. I'm going to go to the slide with the maths. There it is. Okay, so essentially, if you assume a plane stress, so we assume sigma z equals 0, you can rearrange the three-dimensional Hooke's law to get D0 in terms of the material constants and the d-spacing in the three different directions. So we measured the d-spacing in all three directions and then made the plane stress assumption. Going forward, it would probably be a good idea to prepare a strain-free sample and measure the D0.
And you will now also understand why we have both X-rays and neutrons.
Yes, yeah, exactly. Now, it definitely helps you to understand why you have both and you see the difference between them. Thank you.
Any more questions? Okay, I've got one. The melting on the surface.
Yeah.
How common is that? Okay, aluminium's fairly low melting point material, but how common is it?
It's quite common in almost all of them. The material interaction, the temperature of that plasma is incredibly high. It's in the thousands of degrees Celsius, and so you do end up with that in most cases. But with laser shock peening, we don't have to do it without coating, so we can actually perform LSP with some protective coating like black tape or paint or something, and then that gets burnt up and the actual surface is in better condition, but that's more expensive and takes longer to do.
Yeah. Any idea what proportion is melted, or is it how long is a piece of string?
Yeah, I'm not sure. I think Nick was looking at it, yeah, because it was important for him.
Yeah, so slightly different material. I was working with titanium alloy, TI64, and we noticed that there was surface oxidation that was much more noticeable, of course, than aluminium, but just based on its color. Yeah. It looked a lot worse off, but after sectioning it and having a look at it under microscope, it seems to be very, very superficial. I mean, the effect of it is LSP by definition is a cold working process. It's just the nature of the plasma generation of the surface. So it remains very superficial.
You can actually sand it off very easily, that top layer.
Okay,
yeah.
That's great. Because normally we want to get rid of as cast structures, so it's melted. Okay.
Sorry, just one more question. You mentioned something, and I'm just curious. You said that you can protect it somewhat with a layer, then do the laser shock. Are there any criteria for that layer in terms of the speed of sound in that layer, that in the aluminium?
Not that I know of. One of my friends is looking at that as his master's, so we'll answer that in a year's time.
Okay, well, I'll get an answer to my question, snappy answer to my question next time.
Okay, I do know what is an impact is the dielectric breakdown threshold. So actually, we don't after a certain power intensity, you don't get any effect in the peening anymore because the plasma is being generated in the material instead of on the surface, and that lessens the effects quite drastically.
Right. Okay. That's it. Thank you very much. If you can thank us.
Thank you.
The next one is Dr. Zikona Tetana is going to introduce her focus area, which is carbon nanotubes and strong composites. Oh, she's behind me. I was thinking, where is she?
She doesn't want this.
Good afternoon, ladies and gentlemen. As she has said, my name is Zikona.
I've been told by Jackie to make it very quick because we're running out of time. So I'll do a very brief introduction of the carbon nanotubes and strong composites research. This is our focus area. So this focus area is made up of about 8 interaction groups from 8 universities. We have UJ with physics, mechanical engineering, chemical engineering at Wits, and mechanical and mechatronics at Stellenbosch University, Rhodes University, the School of Chemistry at Wits, and University of Limpopo. Now these are the leading researchers: Professor Kovel, Dr. Malvani, myself, Professor Somnath, Professor Mutu, Dr. Rudolf Erasmus, Professor Pillay from UJ, and Jonathan and Kirtland, Rhodes University, and Professor Krauser and Arab Tiba from UJ, and others. Last year we had 2 more additional members, one from the University of Limpopo, and we're so grateful to have that additional member because they have been inactive since actually the area was formed. So these are the students that are in the focus area. We have Ms. Nigiwa Koza, she's going to give us a presentation, and Ms. Alice Makubane, Thomas Mongwe, Lady Mpafo, Prakash, Tapelo Mufukeng, Sevenzi Meshabalala, William Mugone, Marius Mhuepe from University of Limpopo, and Emily from UJ. So, just to give you a brief background on carbon nanotubes, because that's what, or carbon nanomaterials, that's what our focus area is all about. In the beginning, carbon existed as 3 allotropes, namely diamond, graphite, and amorphous carbon. And then, in the 1980s, other forms of carbon that are called fullerenes were discovered, followed by carbon nanotubes in the 1990s by a gentleman called Kijima. So carbon nanotubes are basically cylindrical forms of carbon that are known to be very strong, even stronger than steel. These materials are famous for their unusual properties. They are very strong, as I've said. They are very flexible, you can bend them, and they have high electrical conductivity, high thermal conductivity. As such, they can be used in many different areas. The other forms of carbon that exist are carbon spheres. So they exist in 3 different morphologies so far: the hollow carbon spheres, the core-shell carbon spheres, and the solid carbon spheres. And these materials have similar properties to carbon nanotubes, such as they also have high surface area and are very useful in many different applications. So, these materials briefly, they are made from a graphene sheet that you can roll to form carbon nanotubes, as the other speaker talked about, the single-walled carbon nanotubes, the double-walled carbon nanotubes, and the multi-walled carbon nanotubes, when you roll a graphene sheet into many or multiple layers. They can also be, the graphene sheet can also be stacked to form carbon fibers, or bent to form those carbon spheres. Now, in nature, the carbon nanomaterials are inert, chemically inert, so you need to functionalize their surface for you to use them post-application. So, we can functionalize these materials using different functional groups, and we can dope them with nitrogen or boron. That is trying to replace some of the carbon nanomaterials, carbon atoms with nitrogen or boron. And the nitrogen doped ones are known to yield N-type conducting materials and also boron-type, P-type conducting materials. So therefore they will be useful in some applications like energy applications. So the group mainly focuses on the synthesis of these materials a lot. And I'm just showing just a few of these materials that are made in the labs and are used post to other applications. So here we have solid carbon spheres, the hollow carbon spheres, and other types of hollow carbon spheres. These are actually doped, boron-doped carbon spheres, some fibers, and some tripod materials with a catalyst inside. So depending on the sort of catalyst you use, or even without a catalyst, and temperature, these can be formed. So, as mentioned before, because of their interesting properties, these materials are applied in different areas, and many of our group members, they use these materials in different applications. So, these are some awards and achievements that we had in 2017. The PhD student received the Saki Postgrad Medal, and the lady there received 2 travel grants, which is good. And Ms. Dutoy from Stellenbosch University won an award on 3D printing. And Professor Covell has got a position as a director at of the postgraduate affairs. We won an award for a paper that we published some years back. And the students won the prize, second prize for PhD, oral presentation, and also masters for poster presentation. And then another student who did honors last year, she won the best presentation in the EMSA 2017. And this is what about we produced last year in terms of the paper and articles. And I would like to acknowledge the following universities and departments. Thank you very much. Oh, sorry. Let me introduce to you Ms. Nikki Koza. She will be talking about the carbon dots, other forms of carbons that we make in the lab. Thank you.
Good morning. My name is Nikki Koza, and I work under the supervision of Prof. Koval. My talk is entitled Synthesis of Carbon Dots for Application as Carbon Monoxide Sensors in Fuel Cells. Now, PEM, or rather, polymer electrolyte membrane fuel cells are currently being developed for applications in power generation of portable, stationary, and transportation facilities. So their development was inspired by their ability to produce electricity from the electrochemical reaction of hydrogen and oxygen. With only water and heat as byproducts, polymer electrolyte membrane fuel cells are highly environmentally friendly. As such, they have been used in place of fossil fuels for power generation and also in place of combustion engines for the propulsion of vehicles. Now, due to safety reasons, PEM fuel hydrogen cannot be packaged into the fuel cells. As such, hydrogen is formed from the reformation of methane and natural gas. The major drawback of this method is that carbon monoxide is always produced as a byproduct. Carbon monoxide is problematic because it binds on the catalyst of the fuel cell, and in doing so reduce the efficiency of the fuel cell. To combat this, a carbon monoxide cleaner has been incorporated into the fuel cell system. In order for this carbon monoxide cleaner to operate optimally and effectively, the carbon monoxide concentration in the fuel stream must be known. As such, this necessitates the need for the development of a carbon monoxide sensor. As relatively new carbon sensing materials, carbon dots have not been used in the application of sensing carbon monoxide for application in fuel cells. This is a typical structure of carbon dot, passivated carbon dots, with the core in the center and the molecular chains on the surface of the C dots. Okay, so C dots were discovered about a decade ago, and since then they've been shown to exhibit the following properties, such as photoluminescence and excellent electron and donor acceptor properties. Due to their appealing properties, they've been applied in various applications. And in our project, in our research group, we have 5 projects on C dots, with my one focusing on the development of a carbon monoxide sensor. Carbon dots are mainly used as carbon sensors through monitoring their photoluminescence in response to stimuli. There are 2 mechanisms in which carbon dots can sense and analyte. In case 1, the photoluminescence is quenched, and in case 2, the photoluminescence is enhanced. Here is an example of how carbon dots have been used previously to sense and analyte. In this case, the blue photoluminescence of the carbon dots is quenched in the presence of copper. It is important to note that in order for the carbon dots to detect and quantify and analyte, the analyte must affect the photoluminescence of the carbon dots in a concentration-dependent manner. The aims of my project is to develop a carbon dots-based carbon monoxide sensor which can sense carbon monoxide in a fuel cell environment. To achieve the aim, I will synthesize the C dots, test them for carbon monoxide sensing, and apply them in fuel cells. So, the synthesis of carbon monoxide can proceed in two approaches. The top-down approach, which entails the etching out of the carbon dot from bigger carbon nanomaterials such as carbon nanotubes, and this is how they were discovered. And the bottom-up approach entails the building up of carbon dots from carbonaceous building materials. Now, the bottom-up approach has several methods in which it can proceed, but I choose to use the hydrothermal synthesis, the hydrothermal treatment, because it produces carbon dots which are passivated in a single step. To investigate the effect of using different reactors as heat sources for the synthesis of carbon dots, I used the microwave, the autoclave, and the reflux to synthesize the C dots. Now, the carbonaceous material of choice in the synthesis of C dots, I used polyethylene glycol. Polyethylene glycol is a polymer with a molecular weight of 400 grams per mole. Now, to kickstart the synthesis, I dissolved the polyethylene glycol in water in a 3:1 volume ratio, took the reaction contents, put them in a reactor, and set the reaction time and power or temperature. After cooling of the resulting material, I purified the C dot solution by filtering with a microfilter. Now, this is how, or rather on this side, that's how the C dots look in daylight, and on the other side, it's how they look under UV light. Thereafter, I take the solution, put it in an oven to dry it. Now, this is the major challenge of my project because it's very difficult to obtain the C dots in powder form, and for the synthesis, I haven't received them in powder form. This is not only an obstacle because it limits the characterization of C dots, but also because in order for me to apply the C dots in fuel cells, they need to be in powder form. Okay, now, shown are the 10 images of the synthesized C dots and their corresponding particle size distribution. The C dots are well dispersed with a narrow particle size distribution. The autoclave yields from the 10 images, the autoclave yields pure C dots, whereas the microwave and the reflux methods seem to produce carbon spheres, small carbon spheres as impurities. Now, the autoclave yields the smallest carbon dots with the size of 2.5 nanometer, followed by the microwave, which yields the 3.3 nanometer sized carbon dots. And then the reflux method, which yields 4.8 nanometer C dots. At this point, I can't conclude on which size of the C dots would be best for my application. Now, on the left, it's the FTIR spectra of the precursor with the corresponding spectral assignments, and on the right, it's the same FTIR spectra plotted on the same axis as the spectra of the synthesized C dots. From this, you can see that the spectra of the synthesized C dots is similar to that of the precursor. These results are similar to those in literature, and the rationale is that during hydrothermal synthesis, the functional units of the precursor are retained on the surface of the C dots. That is, the C dots have functional groups on their surface that have the same nature as the precursor as such, which suggests that the synthesized C dots are functionalized, or rather passivated. So, from this point onwards, please bear in mind that the photoluminescence property of the C dots is the important property that I'm looking at for my application. And this is the UV-vis absorption spectra and Apl emission spectra of the synthesized C dots at 350 nanometer excitation wavelength. The C dots exhibit an absorption peak at 200 nanometer, which is ascribed to the formation of multiple aromatic chromophores on the C dot. And they also have edges at different wavelengths, which are ascribed to the pi 2, pi sigma transitions on the C dots. When excited at the 350 nanometer, the carbon dots exhibit photoluminescence at the following positions. Unfortunately, I did not run the spectra at the same concentration of the C dots. As such, I cannot make correlations based on the intensity of the PLs. Now, this is the Apl emission spectra of the autoclave synthesized C dots at various excitation wavelengths. It is interesting that as the excitation increases, the emission of the C dots shifts to higher wavelengths with decreasing intensity. These results are well reported in literature, and it is this excitation-dependent character of the C dots which displays the photoluminescence tunability property of the C dots. It is important to mention that the microwave and the reflux synthesized C dots also showed the same properties. So now, in order to quantify the quantum yield strength of the C dots, I use quantum yield percentage. Quantum yield is, by definition, the fraction of photons which are absorbed that then give off the emission when excited at a particular excitation wavelength. So you calculate the quantum yield using a standard and this equation. These were the determined quantum yields, and even though they are much less than the quantum yield increases with the size of the C dots, as such resulting in the reflux C dots having the highest quantum yield. This means that for application, the reflux C dots would probably be the best ones to use, since I am focusing on the photoluminescence property of the C dots. Now, the conclusions I've made on the synthesis part of my project is that the polyethylene glycol can be used as the carbon precursor and a passivating agent for the synthesis of carbon dots, and this is done in one synthesis procedure, which is very good. And then the autoclave produces the smallest and the purest carbon dots. All the synthesized carbon dots exhibit a excitation-dependent photoluminescence. And last but not least, the reflux method produces the carbon dots with the highest quantum yield. Nevertheless, I would like to purify the sample to confirm this statement. I would like to, or in future, I would like to apply the synthesized carbon dots in fuel cells, and that's the end of my talk. I would like to acknowledge my supervisors for their excellent supervision, the Carbon Dots Group, and the Center of Excellence for funding. Thank you.
Thank you very much for a very nice presentation. Are there any questions?
Yes.
I'm trying to understand something about the structure of the spectral C dots.
Yes.
Are they clumps of amorphous carbon, or are they closed cages of like fullerene or something?
It's a cluster of amorphous carbons, which is like a solid sphere, but smaller.
How come they don't come together? Why do they remain separate? It's kind of...
Oh, they are separated due to the functional groups on the surface of the C dots. It keeps them apart. The minute you try and remove the functional groups, maybe through or when you remove the functional groups through heating them up, they cluster together. Yes?
So I didn't quite get, so what will happen now is the carbon monoxide will attach to the functional group, and that will change the intensity of the luminescence.
Yes.
Is that how it's supposed to go?
Yes.
Not a wavelength shift, just the intensity drop.
Sorry?
Just the intensity drop that you would expect.
Ideally, that's how they've been used in literature. They just reduce the intensity or enhance it, in any case, proportional to the concentration of the carbon monoxide.
Any more? Yes, right at the back.
Thank you. I would like to know what concentration is detectable in, or rather will be detectable using the C dots in the fuel cell?
At this point, I cannot say that because I haven't done the actual tests. But ideally, I'd like the sensor to detect ppm levels of the carbon monoxide, because that's the carbon monoxide that's toxic to the fuel cell.
Do you think, despite what we saw with the photoluminescence, do you think by any chance the size of the dots are they anyhow related with the acceptable, detectable concentration of CO in the fuel cell?
I think so, yes, because the quantum yield, that is the strength of the photoluminescence of the C dots, is related to the size of the C dots. And the higher the quantum yield of the C dots, the lower the concentration of carbon monoxide that can be detected.
Okay, are there any more questions? Okay, let's thank our speaker again. Sorry, desperately trying to finish that. Our last focus area to present is ceramics. And it's not going to be Professor Segalis who's introducing it, because he's having an eye operation and he has my sympathy for that. It's going to be Dr. David Whitefield, and it's the first time we've had him here to introduce it. So take it away.
Thank you, Leslie. Good morning, everybody. No, I don't want the microphone. Thank you. Where's the...
Need it. Need the mic for the...
No, thank you.
It's okay.
Clearly it's the first time and it's confusion reigns. It's off. Okay, we'll try that again. Okay, so it's in the ceramics group, and our purpose is to train students in ceramics and get guys that are qualified and suitably qualified for industry, and to get them out into industry as good engineers from the Wits University. Our other aim is to conduct world-class research in ceramics, and it should be tied very closely to our industry in South Africa. There's no point in producing research if it's purely academic. Industry will not fund it, and therefore we tend to like to have collaborative partners that we can actually work with. Oops. So under our scope, what we're covering and what we are currently working on are projects in amorphous glass for the bio prosthetics replacements, high temperature ceramics, 3D printing, we'll come to that in a bit more detail just now, castable pyrophyllite ceramics, armor ceramics, in other words transparent ceramics, which will provide windows for tanks and the like, electro ceramics, and our current activities are covering materials development and the structure and properties, as well as obviously measuring all these things. Once we've made them, we need to be able to tell people what they can do and what they can be used for potentially. The equipment that we've got and we're using in our section covers a wide variety of powder metallurgy processing kit, from milling, powder characterization. We've got furnaces, some spark plasma sintering furnaces, which go up to 2,400 degrees, some regular muffled tube furnaces, which we get around to about 2,200, and pressures of about 100 megapascals. We also have a very nice instrumented or CNC controlled lathe. Our members include Professor Segalis, Professor Masura from Tampere in Finland, Dr. Matthias Herman from Dresden, Debbie Blaine, Kenneth Azamena, Ian Botev, and Cuthbert, forgive me for the surname.
Chicken.
Nagapinga Gendu, forgive me, Cuthbert. Our students, we have 6 active students at the moment, doing various research into the topics we described. There are 2 postdocs with us. 2 students are doing their final write-ups, and there are 5 students in various stages of completion in their MSCs and PhDs in our group. The next person you are going to hear from is Ms. Cindy Antonisa, and she's looking at gel casting coupled with 3D printing for some very exciting developments there, but I'll leave that up to her to describe to you. These are some of the SEM pictures that she's taken, and you can see some very nice aluminum microstructures. Unfortunately, there's still a bit of porosity, and I'm sure Cindy will let you know how she's going to overcome this. And these are some of the final prescribed parts that we would like to actually make out of 3D printed gel cast ceramics. Not necessarily light bulbs, but in that form, in that shape, or as an impeller, something along those lines. So complex shapes are quite attainable. Our 3D printing has all been kindly done for us by Mr. Lucas Janssen van Rensburg here. And what he has proved is that with a very cheap setup, you can actually achieve a hell of a lot. It's been done. We have printed various shapes. We have even linked chains together, chain links. And it can be done relatively cheaply, cast, and then made into something fully functional. The work that Mr. van Rensburg, Janssen van Rensburg has been busy with is about coatings, and he's printed out ABS coated or ABS material, and he's coated it with zinc, nickel, copper, and the like. These things he has then tested to see what the adhesion properties are of these materials to these various substrates. And this is an ongoing experiment in our section as well. There we have some of the samples that he's printed out and coated, and those are the lugs that he adheres to them with literally epoxy, and then pulls them off, takes a measurement, and determines which coating has the highest adhesion. That would be the sort of structure, the basic design of how all the peoples in our group fit together. As you can see, it is quite complex, ranging from industry down the bottom left with element 6, through to other universities overseas. It is a rather complex structure. I won't get stuck into that just now. And then thank you. Hopefully that was a good introduction to our ceramics department.
Good day, ladies and gentlemen. My name is Cindy Dinesa, and I'll be presenting to you on the gel casting of alumina by using 3D printed molds. So, just for a brief background on ceramics, these advanced ceramics have found applications in various industries. This includes the medical field, electronics, as well as the defense industry. And on the figure there we can see the various uses of ceramics. They can be used in optics as high pressure highlight lamps. They can be used in the medical field as medical restorations, and that's a hip replacement. And in the automotive industry, they are used as catalytic converters. They possess properties such as low weight, high hardness, corrosion resistance, as well as chemical stability. The current challenge is the low-cost fabrication of complex-shaped alumina parts. Because of the high hardness and the low fracture toughness, the machining of already sintered parts has become difficult, time-consuming, and expensive. Therefore, this has led to the development of near-net-shaped colloidal forming processes. So colloidal forming processes can be defined as liquid-based shaping methods that involve the preparation of a suspension. So the suspension is prepared by mixing a ceramic powder with a dispersant, a coagulating agent, as well as a solvent. Once the suspension has been formed, it is then poured into a mold to get the desired shape. This can then be dried and sintered to form a dense part. And these processes here are the process based on colloidal forming. This includes slip casting, tape casting, as well as gel casting. The challenge is that all these processes require a fabrication tool in order to produce the desired shape of the ceramic part. However, the time and the expense needed for the machining of the part then increases the overall cost of the process. So in this work, gel casting has been chosen as the forming technique. So gel casting was chosen because it enables the use of high solids loading. This leads to parts with a high grain density. Therefore, they are easier to handle and also machine while they are still on the grain state. For gel casting also, there's a shorter binder removal time because the polymers that are added in the suspension are about 4 weight% of the powder. Most importantly, the shaping for gel cast parts is easier because there's a variety of mold selection. This includes molds based on cheap metals such as aluminium. Plastic molds can also be used as well as wax-based molds. In this case, 3D printing was used as a form of rapid tool fabrication. This is where the mold is printed using a computer-based design model. This was chosen because 3D printed parts have been used in various industries, and they have shown that they have the necessary strength and performance. They can also be easily integrated into current processing techniques. And if there's any need to change the mold, this can be done electronically rather than physically. This then eliminates the time and the expense used in the machining of the part. So the aim of this work is to determine the accuracy with which ceramic parts can be fabricated using gel casting as well as 3D printed molds. And this will be achieved by addressing the following objectives, that is to produce an alumina parts by the process and to investigate the effect of the solids loading on the densification as well as the physical properties of the parts, and to test different monomer systems. So the experimental procedure was as follows. For the 3D printing procedure, the mold was designed using a computer-aided design software where an STL file was produced, and then this was sent into the printer, which printed the object layer by layer. For the mold material, ABS plastic was chosen. This was chosen because it is cheap and it is easier to print. It is available, and most importantly, it can be dissolved in cheap solvents. Therefore, it makes the demoting process easier, which is valuable when producing complex shaped parts. And the gel casting procedure. So 2 monomer systems were tested. The first monomer system that was tested, it was hydroxyl methacrylate, which was cross-linked with methylene bisacrylamide, and this will be termed HEMA. And the second monomer system was a copolymer of isobutylene and maleic anhydride, and this is commercially known as isobam. So the suspension was formed by mixing the monomers with deionized water and ceramic powders. The ceramic powder was varied between 40 volume percent and 60 volume percent. These were milled in a planetary ball mill for 24 hours to achieve perfect mixing and break any agglomerates on the powder. After the mixing, the powders the suspensions rather underwent rheological testing in order to determine the viscosities, which will make it easier to pour the suspensions into the mold. And prior to the casting procedure, all the suspension had to undergo de-airing. This was to remove the air that was trapped in the slurry because the trapped bubbles end up causing porosity in the final parts. This was done in a desiccator which was connected to a vacuum pump. For the HEMA system, a catalyst and an initiator are required to polymerize the monomers and form a gel. Whereas for the isobam system, the gel is formed in room temperature, so there is no need for a catalyst or an initiator. So after the parts were cast, they were left in air for about 20 minutes, where the monomers were then polymerized and a gel was formed, and the demolding process took place. The demolding was performed by dissolving the mold in a certain solvent. This left the green parts intact. They were then dried in controlled environments. And before the sintering process, the polymers that were added on the suspension need to be bent off, and this was done according to the binder bend out and sintering profiles seen at the corner down there. The binder bend out process was at 600 degrees Celsius for a period of 60 minutes, and all the parts were then sintered at 1650 degrees in air for 3 hours. So characterization was done by doing the density measurements on both green parts and sintered parts. The hardness and fracture toughness of all the sintered parts was done by Vickers indentation, and the fractured surfaces of the parts were observed by scanning electron microscopy. And the results. The rheology of the suspension was done by a rheometer, and this was to test the ease at which the suspension can be poured into the mold. So all suspensions were found to have a shear thinning behavior, and this is beneficial for gel casting. And as it can be seen from the graph, the viscosity is plotted as a function of the solids loading. This line here is for the isobam monomer system, but the viscosity seems to increase with an increase in the solids loading. Moreover, isobam has a low viscosity as compared to the HEMA system, where at 50 volume percent solids loading and 60, there is a very high viscosity. So this high viscosity led to difficulties in the de-airing process, as well as in the casting behavior of the slurry. And this graph shows the effect of the solids loading and the monomer system on the density of the dried grain bodies. For the isobam system, it gives relatively a high grain density at 40 volume percent solids loading, while the HEMA system had a low grain density. But at high solids loading, the relative densities are almost similar. And the sintered density of all parts is plotted as relative density against the solids loading. It can be seen here that for 40 volume percent on the parts cast by using HEMA, the relative density was low, that is at 93%, whereas for isobem, high relative densities were found. It is at just below 98%, and at 60 volume percent, the relative density was above 98%. And then at 50 volume percent for the isobem system, the decrease in density can be attributed to insufficient dearing. Therefore, there was high porosity on that part. And then the hardness of the materials was tested by viscous indentation. At 40 volume percent of the HEMA, of the part produced by HEMA, the hardness was found to be 13 gigapascals, and this may be due to the fact that the relative density was low as well at 93%. However, for all the other parts, as it can be seen from the error bars, that they have relatively a similar hardness, which is between 15 and 18 gigapascals. This hardness is similar to hardnesses found in literature for alumina sintered via pressureless sintering, as it is known that hardness usually decreases with an increase in grain size. And the grain size of parts produced from 60 volume percent alumina was estimated to be about 5 micrometers. And on these images, it can be seen that there is a high porosity on both systems, while the HEMA system had more porosity compared to the isobem system. And this is due to the fact that there was insufficient dearing due to the high viscosity of the slurries. Both intergranular and intragranular pores can be observed on all. And just to conclude, alumina parts were successfully gelled and demolded without causing any fracture. The dried grain parts were strong, they were suitable for handling and machining. Higher solids loading was found to be beneficial for both densification and mechanical properties. Isobem was found to have an advantage over HEMA in that there was only one additive that was required. And for future work, the effect of the 3D printed molds will be investigated on the surface finish of the parts produced, and the dearing process also needs to be improved in order to remove the trapped bubbles, and we need to investigate the effect of the machining on the grain bodies, as well as the production of the complex alumina part, as Dr. Whitefield shown on his. And I would like to acknowledge the following people. And thank you.
Thank you very much for a really nice presentation in a really exciting field. Yeah, scary. Okay, let's go for some questions.
Sorry, it's me again. You mentioned at one stage that you have high viscosity, which poses a problem in certain circumstances. Something I don't quite understand here that you can help me with. Couldn't that viscosity is very sensitive to temperature? Couldn't that just be controlled by heating?
Okay, the issue with heating is that the gelation process can be activated by either an increase in temperature or the use of an initiator or a catalyst. So if we heat up the slurry, it can end up being, the polymerization will occur before the bubbles can be removed from the slurry.
Okay. Any more questions? Okay. How stable are these things? You said you can handle them, but can you leave them on the shelf for a little while or not?
The grain bodies?
Yeah.
Yes. Once they are dried, they are relatively, because I was able to even carve them and polish them. but the wet bodies are a bit sensitive.
Right, okay.
They're a bit sensitive, but when you were dissolving the mold, they were still intact, the wet bodies, yes.
And is there a price difference between your two choices?
Yes. For the HEMA system, you need about 5 additives, and for the isoben system, there was just only 1 additive that was added.
So that determines the
Yes, that determines the overall price.
Great. Okay, last chance for anybody? No? Thank you very much. All right, just give us a second or two. Right, we're not sure whether the Dean of Science is coming back, but we'll give him a second or two, and if he doesn't, I'll make up something. Okay, we're going to do this in a slightly different way, partly because we're one person down, partly because we're one person down, partly because we've overrun, and we've got to start our steering committee meeting a different way. So, while Jackie's adding up the last scores, I could tell a joke, but I'd probably get arrested, because it would probably be not a nice joke. So I'd rather not do that. We don't want to do that anyway, because we're running out of time. So what we're going to do is, instead of giving out the certificates individually, okay, so I'm sorry you miss out on the humour of me totally messing up all the names. We're going to get around that, thank goodness. What we're going to do is, the focus area coordinators are going to come and collect them, and while you're clapping for the focus area coordinators, you're really clapping for the students, okay? So we're going to get the students to stand up while the focus area coordinators come down. So, for case, can we have Professor Natasha Sachs, and can the students stand up, please? Yeah. Sorry, we haven't got tea while we walk around. The next one is carbon nanotubes. And if Dr. Sikona Tetana can come down, and I know where she is now, and if the students can stand up, well done. Next one is ceramics. We're doing this in alphabetical order in case you hadn't noticed. So if the students can stand up, please. Next one is Die Hard. Very short return. Students, all stand up. Then we have ultra hard materials, please. And Robert might need you if you're still here. No such thing as a free lunch. Well, there's not even a free lunch, so it's fine. So students, stand up, please. Thanks for coming. And lastly, it's strong metallic alloys. Students, stand up. really good hand of applause. And also, yay! I thought the posters were very good this year. There wasn't one I sort of thought, ooh, don't like this one. No, they were all very good. And then the talks as well. Thank you very much. So let's give a hand to the talks. And last but not least is thank you to the supervisors. Okay? Because without them, you'd be up the creek without a paddle. Even though they might get on your nerves from time to time. Are we ready, Edward?
I have 3 more. Who is Abraham?
Okay.
Why you can't give me that job?
Yeah.
I'll try not to mess this up. Right. You might notice I've got 3 bits of paper. Sorry. Right, for the poster. That's allowed. The poster is entitled The Synthesis of Carbon Nano Onions Using Flame Assisted Method. It sounds like a restaurant, doesn't it? And I'd like my carbon nano onions medium rare. You will be getting a better version of this, and all the prize winners are going to get 1,000 rand. Right. We have 2 pieces of paper here. Okay? That means a tie. And they're still going to get 1,000 rand each. And they're going to get a nicer certificate as well, because we haven't had time to write in the title yet. So I'll just give you the winners. Dramatic pause. Liberty Capizzi and Sean van Staden. Yes! Okay, and we still haven't got a dean, so I'm going to say thank you very much for people for coming. I thought it was a very nice presentation of results. And thank you to everybody for all the efforts. Thank you to Jackie. And for those of you who might not know yet, Jackie has taken over from Casey. Okay? So that makes Jackie even more scary than she was. And also, she's not here, she's on leave, but you all know that Marina has put in an awful lot of work and helps us all out and sorts out who gets what funding and actually gets there. So thank you very much for coming, and without a dean here, I'm going to close the proceedings. Thank you.
Thanks you. See you. Sure.
Thanks very much, eh? Bye. Cheers.
Cheers.
I'm going to see if I'm going to get film. Yeah. But the other one, I think it's oh, that's fine.
And then the linear is over a 3-step. Should this name on my carrot? Oh,
Cool.
do you need anything from me? Do you need anything?
Were you?
That's for Phyllis. Sorry, we were just running out of time. No, we thought. Okay. Thanks very much. Thank you.
Cool. See you next time.